The indispensable role of twin aircraft simulators in modern aviation. Twin aircraft simulators have evolved from basic flight trainers into sophisticated, high-fidelity replicas critical for the safety, efficiency, and continuous advancement of the aviation industry. These advanced simulation environments are not merely tools for pilot proficiency, but are foundational elements in the entire aircraft lifecycle, from design and development to operational training. Their impact is profound, driving significant improvements in safety, optimizing training methodologies, and yielding substantial cost reductions across the board. The pivotal role in pilot training and aircraft development pilot training. Twin aircraft simulators are the backbone of modern pilot training. They provide a safe, controlled, and repeatable environment to practice routine operations, may master complex maneuvers, and, crucially, handle emergency procedures that would be too dangerous or impractical to perform in actual aircraft. This allows pilots to enhance safety, develop muscle memory and decision-making skills in high-stress situations without risking lives or expensive equipment, achieve high proficiency, practice takeoffs, landings, instrument flying, and systems management to a level of mastery, experience diverse scenarios, encounter a vast array of weather conditions, air traffic control challenges, and system malfunctions that would be impossible to replicate in real-world training within a practical timeframe. Facilitate type ratings and recurrent training. Qualify pilots on new aircraft types and ensure ongoing proficiency, meeting stringent regulatory requirements. Aircraft development. Beyond training, simulators are indispensable during the aircraft development phase. They enable engineers and test pilots to validate design concepts, test aerodynamic models, flight control systems, and human-machine interfaces early in the design process, identifying potential issues before physical prototypes are built. Integrate systems. Evaluate the interaction of various aircraft systems, avionics, propulsion, hydraulics, in a simulated environment, reducing integration risks and costs. Gather early feedback. Allow pilots to fly the aircraft virtually, providing invaluable feedback on handling qualities, cockpit ergonomics, and system functionality, informing iterative design improvements. Reduce physical testing. Minimize the need for costly and time-consuming flight tests by conducting extensive virtual testing, accelerating development cycles. The importance of adhering to the ASTM SX000I standard. The increasing complexity of modern aircraft and their associated simulation environments necessitated a standardized approach to information exchange. This led to the development of the AAIA ASD SX000I International Specification for Integrated Product Support. While primarily focused on product support, its underlying principles for information management are vital for simulation environment development, particularly regarding data consistency and interoperability. As part of the broader S-series of international specifications, like S1000D for technical publications, aims to standardize the content and format of information across the life cycle of complex systems. For simulation, this translates to structured information exchange, ensuring that data relevant to simulation, aircraft characteristics, system models, maintenance procedures, operational limits, is managed and exchanged in a standardized machine-readable format. Data integrity and consistency, reducing errors and ambiguities that can arise from disparate data sources and formats, ensuring that the simulator accurately reflects the real aircraft. Long-term supportability, facilitating the update and maintenance of simulators throughout the aircraft's operational life as new information or modifications become available. How SX000I contributes to efficiency and interoperability. Adherence to the SX000I standard significantly boosts efficiency and interoperability in the development of new aircraft systems and training programs. Model-based definition integration. SX00I encourages the use of MBD principles, where 3D models and associated data are the authoritative source of information. This allows simulation developers to directly leverage design data, ensuring high fidelity from the outset. Seamless data flow. By standardizing data formats and exchange protocols, SX00I enables a seamless flow of information between design, manufacturing, and simulation teams. This means that changes made during aircraft development are quickly and accurately reflected in the simulator, preventing divergence between the physical and virtual assets. Real-world applications and benefits of SX00I compliance simulators. While specific public case studies explicitly detailing SX00I compliance for simulators might be proprietary, the principles of SX00I are widely adopted in major defense and commercial aerospace programs. The benefits are seen in integrated fighter programs like the F-35 Joint Strike Fighter. These programs rely heavily on digital twins and highly integrated data environments. An SX00I-like approach to data management ensures that the vast amount of design, maintenance, and operational data can be directly fed into simulation systems. This enables first flight-ready training. Pilots begin training on high-fidelity simulators even before the first physical aircraft takes flight, using validated flight models and systems derived directly from engineering data. Cost-effective upgrades. When new software blocks or hardware modifications are introduced to the aircraft, the standardized data exchange facilitates rapid and accurate updates to the simulators, minimizing downtime and costs associated with training gaps. Commercial airliner development, like the Boeing 787 and Airbus A350, modern commercial aircraft development cycles are incredibly demanding. Adopting standardized information management helps in accelerated certification. Simulators used for certification are built with data directly traceable to the aircraft's design specifications, streamlining the regulatory approval process. Global training networks. Airlines operating these aircraft globally benefit from consistent training content and simulator fidelity, regardless of their training center's location, due to standardized data packages. Maintainability and logistics training. Beyond flight simulation, the data consistency enforced by SX00I aids in developing maintenance simulators, allowing technicians to train on virtual replicas using accurate standardized maintenance procedures. This reduces errors and improves readiness. The core benefit is that the digital data used to design, build, and maintain the aircraft is the same data used to create and update the simulator, fostering a single source of truth and drastically improving fidelity and efficiency. Future prospects and advancements in twin aircraft simulator technology. The future of twin aircraft simulators promises even greater realism, adaptability, and integration driven by emerging technologies. Immersive technologies, VR, AR, MR, virtual, augmented, and mixed reality will move beyond visual systems to create fully immersive training environments. Pilots could interact with holographic cockpits or perform walk-around inspections in AR, blurring the lines between physical and virtual training. Artificial intelligence and machine learning, adaptive training. AI will personalize training paths, adjusting scenarios and difficulty based on individual pilot performance, optimizing learning outcomes. Intelligent adversaries. AI-driven virtual instructors and air traffic controllers will provide more dynamic and realistic training interactions. Predictive maintenance for simulators. ML can analyze simulator performance data to predict component failures, enabling proactive maintenance and maximizing uptime. Cloud-based simulation. Moving simulation platforms to the cloud will enable greater accessibility, scalability, and collaboration. It will allow for distributed simulation environments where multiple pilots or even ground crews can train together remotely. Digital twins and persistent data models. The concept of a digital twin, a living, dynamic virtual model of a physical aircraft, will become even more ingrained. Simulators will increasingly become direct interfaces to these digital twins, ensuring perfect fidelity throughout the aircraft's operational life. Enhanced haptic feedback and motion systems. Advances in haptics will provide more realistic tactile feedback for controls, while motion platforms will continue to evolve, offering wider envelopes of motion and improved responsiveness. Integration with real-world operations. Simulators will increasingly integrate with live operational data, allowing for what-if scenario planning, mission rehearsal, and even real-time operational support for complex missions. These advancements will lead to even more efficient and effective training, further reducing reliance on costly flight hours, improving pilot readiness, and enhancing overall flight safety. Standards like SX00I will become even more critical in managing the exponential increase in data and complexity that these future technologies will introduce. Conclusion. Twin aircraft simulators are far more than just training devices. They are strategic assets underpinning the safety, developmental efficiency, and economic viability of the aviation industry. From enabling pilots to hone their skills in a risk-free environment to validating complex aircraft designs and systems, their utility is unparalleled. The adherence to rigorous standards such as AIA Honshi ISD SX00I further elevates their value by ensuring data consistency, interoperability, and long-term supportability. As technology continues to advance, these sophisticated simulation platforms, driven by immersive experiences, artificial intelligence, and cloud computing, are set to redefine the boundaries of aviation training and development, cementing their indispensable role for decades to come.